Hi everyone. It's a beautiful day here in northern Kentucky. In the background you might hear the hum of lawnmowers as my neighbors are mowing their lawn, or my dog barking as he lets everyone know who's boss here in this neighborhood. Today we're going to focus on two proportions and how you compare two proportions. For the methods that we focus on in this class, the two proportions the samples from the two proportions have to be independent. Remember that independent samples are samples where the selection of one sample is unrelated to the selection of the other sample. There's two methods for making inferences. One is you could answer questions about population proportion 1 and population proportion 2. Is proportion 1 greater than proportion 2 or less than proportion 2 or not equal to? You could also try to estimate, and that would be a confidence interval, the difference in the population proportions. So let's look at an example. So a research question focusing on pregnant teenagers and those who receive nutrition education and those who don't. Do teens that receive there's my dog. Do teens that receive nutrition education produce a lower proportion of low birth weight babies than do teens who receive no such education? So the nature of this data, which is one of the key questions you need to ask, what are we asking? We're saying you have a baby, you've got two groups, those that receive nutrition education, those that don't. You would then record they have a baby weight, and you would record the weight as, is it a low birth weight baby? So it would be put into one category versus is it not, is the birth weight in a normal range? So to conduct the study, 314 pregnant teens were selected, and of the teens that were selected, a total would be 630. 314 were randomly assigned to receive nutrition education. 316 received no such education. Here's sort of an overview, a visual of what we've got. We've got the population of interest is all pregnant teens. Population 1 would be a subgroup of those that receive nutrition education. Population 2 would be those that don't. We're trying to compare the P1, remember P is the population proportion, so the proportion of all low birth weight babies among population 1 versus population 2. To make inferences, we can use a hypothesis test or confidence interval. From the populations, we draw samples. Sample size from population 1 is N1. The sample proportion is X1 over N1. X1 is the number of successes. Okay, success in this case just means what you're looking for. Okay, so in this case we're looking for low birth weight babies. So there's a baby born to a teen, and the question that what you'd record in your spreadsheet would be, is the baby low birth weight or not? So it would be a yes or no. For sample 2, we have N2 is the size of sample 2, and P hat 2 is the sample proportion in sample 2. Okay. So for testing, for doing a hypothesis test, we're going to test for equality. Okay, equality would be, basically we're going to be skeptics. The null hypothesis is that P1 equals P2. So in other words, there's no difference in the proportion of low birth weight babies among the two populations. That would be, if you did the subtraction, P1 minus P2 is 0. Or you can ask whether P1 minus P2 is greater than 0. In other words, the proportion among those with education, proportion of low birth weight babies is greater than that in proportion in population 2. Is it less than the proportion in population 2? And this should be a not equal to, which I'll change right now. Sorry about that. Let's see. My not equal to symbol. There we go. And insert. Okay, that was a quick fix. Sorry about that. Now the validity. Remember, this test is going to be based on the fact that both the sampling distribution of proportion 1 and proportion 2 are normal, and that would be that N1 times P1 hat is greater than 10, N1 times 1 minus P hat is greater than 10. So they're basically validity conditions for the individual proportions. N2 P2 hat's greater than 10, N2 1 minus P2 hat's greater than 10, and the samples are randomly selected. If that's the case, we would find some estimate of the difference in population proportions, P1 hat minus P2 hat. If the null hypothesis is true, then these differences are going to be 0. What we found is that from our sample, we find a P1 hat minus P2 hat. We need to find the z-score of that. The z-score is going to be the thing, as I always like to say, P1 hat minus P2 hat minus what we think the mean of the things is, and that would be 0, over this expression, which is a standard error or the standard deviation of the difference in proportions. P1 hat in this case is called a pooled proportion. It's the number of successes in group 1 plus the number of successes in group 2 divided by the total number of cases that were examined. Okay. So for a confidence interval, it's very similar. You have the same validity conditions. In general, for a confidence interval, you've got the estimate, the thing, as I like to say, plus or minus. In this case, since it's a normal distribution for the P1 minus P2 hats, we have a z confidence value, how many standard deviations we need to go up and down to collect or to capture 95 or 90% of the data, times the standard error, the standard deviation of the thing. In this case, it would be P1 hat minus P2 hat plus or minus some z confidence value times the standard error, which is given by this expression. Remember, the z confidence values, how many standard deviations we need to go up and down. If it's 90%, it's 1.645, 95%, it's 1.96, and 99%, it would be 2.578. Okay, so getting back to the example at hand, we have defining the groups. P1 we'll call the proportion of babies with a low birth weight born to teens who completed nutrition education. P2 is the proportion of low birth weight babies for those who did not receive nutrition education. Now, we've talked a fair amount about Statcrunch, and with 2 samples, we're going to be doing most of the calculations by Statcrunch. Still want you to set up the hypotheses and decision rule and so forth. In this case, the hypotheses, again, being skeptics, that the proportions in the 2 groups are the same, versus we conjectured that those who received the education, the proportion of low birth weight babies among that group would be less than the proportion of low birth weight babies among those who received no nutrition education. And remember that Statcrunch turns this into basically differences, subtracts P2 from both sides, so P1 minus P2 is equal to 0 versus it's less than 0. Oh, excuse me. Must be something outside. All right. The decision rule is reject H naught if the p-value is less than 0.05. The test statistic, since it's a hypothesis test for 2 proportions, qualitative data is z equals P1 hat minus P2 hat, and essentially what we've talked about before. Notice on the formula sheet it does not have the subtract 0. It's there. This is the thing minus what we think the mean is, which is 0. Now, just to show you that this is not impossible to do by hand, I'll do this one by hand. P1 hat, so from our basically from our data, 23 of the 314 teen mothers that received nutrition education had low birth weight babies. 39 of the 316 in the non-instruction group had low birth weight babies. So our P1 hat would be 23 out of the 314, which is essentially 7.32%, or as a proportion 0.0732. For the group that did not receive the education, it's 39 out of 316, or 0.1234. Our P hat in this formula, which we need to calculate this standard error, is going to be the number of successes in each group, 23 plus 39, over the total number. Again, that's a pooled percentage of successes, quote-unquote successes we found. That's 0.0984. Now, plugging all of that into the formula, what you get is you get P1 hat minus P2 hat divided by the P hat times 1 minus P hat times 1 over N1 plus 1 over N2. When I do the mathematics for that, I get Z is a negative 2.11. The difference in the sample proportions was negative 0.05. So essentially the population or sample 1 had about a 5% lower incidence of low birth weights than the sample 2. Again, this is less than what, if the groups are truly equal, you'd expect those to be about 0. So our p-value is finding essentially what is the chance of finding that difference, or something less, because we're looking for evidence that the proportion is negative, that it's less than 0. So we'd find this p-value right here, highlighted in red. Now let's go to Statcrunch so we can show you how to do that with Statcrunch. Sorry. There we go. With Statcrunch, it's a proportion statistic to sample, and we don't have the data, but we've got a summary of the data. So among group 1, we had 23 low birth weight babies out of 314 cases. For group 2, we had 39 low birth weight babies out of 316 cases. The hypothesis test is that the groups are the same, P1 equals P2, or P1 minus P2 equals 0, versus P1 minus P2 is less than 0. Compute, and you come up with your Statcrunch table, which looks like this. Okay, your Z statistic, which we came up as 2.1 when we did it by hand. This is what confirmed it here, and our p-value. Now I'm going to go back to the table because I've copied that table into here. So here's the Statcrunch results. What we found, a p-value of 0.017 with our level of significance of 0.05. We do reject H0. Thus, we can conclude that the proportion of all teen mothers that receive nutrition education have low weight babies is less than the proportion of all those that receive no nutrition education and have low weight babies. In other words, nutrition education among teen mothers seems to result in nutrition education seems to result in an increased proportion or decreased proportion of low weight babies, or an increased proportion of healthy weight babies. Okay, now what if I'd said, instead of testing whether there is a difference or whether one's greater, if I just said let's estimate the difference in the proportions? That would be with 95% confidence, that would be a confidence interval for the difference in proportions. The formula, which I'd like you to list, is here. Using the data that we've calculated for this, you've got that the difference in the sample proportions plus or minus the z value, and then this over the times the standard error. And so, I mean, you can do this by hand, confirming that on Statcrunch. And again, I'll go back to Statcrunch to show you how. If I pull up Statcrunch, if I go back to options and edit, and instead of doing the hypothesis test, I do the confidence interval and compute, and my results are basically a negative 0.96 to 0.0038. Okay, now going back to the Statcrunch, what I've got there is Statcrunch results for the confidence interval. Again, you don't need to do it by hand, but I just want to show you that it is possible. What we've got is with 95% confidence, we can conclude that the difference in the proportion of low weight babies among all teen mothers that receive nutrition education, which is population 1, and all those that receive no nutrition education, which is population 2, is between negative 0.0965 and negative 0.0038. That would be fine. You could leave it there. I always like to sort of interpret that in terms of this problem. So in other words, this suggests that for pregnant teens participating in the nutrition education program, we estimate that the prevalence of low birth weight among their babies is between 0.39 and 9.85 percentage points smaller or less than teens that receive no such education. Lastly, focusing on validity. Validity, which the conditions are listed here, and they're on your formula sheet. 314 times P1 hat, which is 23 over 314, is 23. It's bigger than 10. For sample 1, P1 hat times 1 minus N1, excuse me, times 1 minus P1 hat is 291. It's also bigger than 10. Do the same thing for sample 2. We have a random selection of teen mothers that completed nutrition education and those that did not, so this process is valid.